Hello all. So we are going to solve today's Leetcode problem. Implement queue using stacks. So this is an easy problem, but I would consider it medium because it's a little bit tricky. If you read the question properly, you can see that implement queue using stacks, not a stack. Stacks, multiple, right? So that means we need to use one or more stacks to implement the solution. So basically we need to use two stacks. So here we need to implement queue using two stacks. Okay, we will have stack 1 and stack 2. So but before that we need to understand what's a queue and what a stack is. I'll give a simple rough idea. So first we'll understand what's a queue. So for any data structure like queue and stack, there are four operations. Okay, four operations. The main one are push, second is pop, third is peek, and fourth is empty. What is push? Push means we are inserting elements into the data structure. Okay, pop means we are removing element from the data structure. Peek means we are seeing, like we are peeking the top element which is present in our data structure. Empty means we are just checking whether the data structure is empty or not. So these are the four operations. So let's understand the four operations for a queue. Okay, we are taking three elements, 1 2 3. Okay, first the queue is empty. Now we'll insert 1. So it will be 1 here. Okay, in the queue we have 1. We are inserting in the first end. Suppose this is the first end, this is the second end. Okay, now if we add 2, what will be? It will be like this, right? 2 and 1. Okay, this is the queue. In queue we'll add elements in one end. So if we add 3, now it will be like 3 2 1, right? This is a queue data structure. This is push. Okay, push, push. Now let's understand pop. So what are we doing in pop? We are removing element from the second end, from this end, pop. So if we do pop on this data structure, the answer will be 3 2. So the element 1 will be popped here. So we are popping from the this end. Okay, now we'll do peek. So peek, what will be the answer of peek? We are looking in from this end. Okay, in peek operation the answer will be 2. Okay, so and empty, the fourth operation is empty. Now is this data structure empty? No, there are two elements 3 and 2, so it's not empty. So these are four operations, and queue is also called first in first out, FIFO. That means whatever element we input here, that will be the one that will be removed at the end during the operation. First in first out. Now let's understand stack. Stack is like a bucket, queue is like a pipe, stack is like a bucket. Now we'll input it from the top. Now there are three elements, 1 comma 2 comma 3. We'll input it 1 2 3. Now if we do pop, what will be the operation? We'll remove it from the top only, right? So the answer will be 3. You can see here, if we do pop operation on the same elements, here the answer is 3, whereas here the answer is 1. Okay, this is the fundamental difference. Now if we do peek, if you do here, you will get 2 only. Okay, suppose if there are 1 2 3 4, and if there are 3 4 2 1, okay, if there is data structure, then we do pop pop. Then if you see, the peak will get changed. The peak will be here 3, the peak will be here 2. Okay, the peak is also changing, pop is also changing. Empty is simple. If we check whether the stack is empty or not. Okay, so stack is also called LIFO. That means last in first out. So we are adding the element 3 at the last. If we do pop, this will be the first element that will get popped. Okay, so this is LIFO. Now we need to implement queue using stacks. So this is the code. We'll first check how to implement this, okay? So now we know that we need two stacks to implement it. Stack 1, st1, st2, okay? For inserting, we'll use stack 1. So if you want to push, we'll use 1, 2, 3. Now, if we do pop, in queue, what should be the answer? This will be the answer, right? 1. The last in, first in, first out. So the answer should be 1. But in stack, if we do pop, we'll get 3 as the answer. So what we do? So we'll put every element in this second stack, okay? This is a stack. So what we get here? st1 will be empty. st2 here will be with the elements like this, okay? 3, 2, 1, right? So we are putting 3 here. Next we are putting 2 here. Next we are putting 1 here. Now if all the elements are drained in stack 1, they kept in stack 2, now we'll get the reverse order. And this becomes queue now. So if you do peak operation here, 1, this will be the answer, right? The correct answer. If you do pop operation also, this is the correct one. It will pop the first element. Okay, so the logic behind is this only. So whatever we do, we'll pop it here and do this. So for push, we use stack 1. When it comes pop or peak, we empty the stack 1, put it in stack 2, and then we get the answer. Okay, now how do we optimize this? So if we do pop, push, pop like that, every time if there is a pop operation or peak operation, we need to empty the stack 1 and we need to put into stack 2. If there are 100 elements, so we are basically what we are doing, we are putting these 100 elements there and we are getting the last one. Is this fast? No, this is not fast, right? For every pop operation, if there are 100 elements or 1000 elements, we are inputting all the elements in the stack 2. It's very time consuming. So we can utilize a simple trick here that we'll understand with this code only. So let's analyze the code here. Let me clean this once. Okay. Okay. So to optimize our approach, we are using this variable front. Okay. So we initialize the stack with the queue with two stacks, stack int st1 comma st2. Okay, so we have two stacks and we have variable also called front. Okay, this is the optimization. I'll show you now. What's the push? Okay, if so normally what we use stack 1 for push, right? We'll do st1 dot push the element x here. Okay, now but we are adding one condition. If st1 is empty, if st1 is empty, that means both are empty here, st1 st2. No, we don't consider st2. If st1 is empty and if you are adding it, then we say that we initialize here front equal to x. Okay, this is the first element that has been added, so we'll keep that in mind here in the first element. Now pop. So in pop, one need to do, we'll check if st2 is empty. Normally in pop operation, what I told, you need to empty the stack 1 and put all elements in stack 2 and pop the element, right? Now what we are doing here, we are checking first whether stack 2 is empty or not. So basically during pop operation, we need to neglect the stack 1 in the optimized approach. So basically saying that we don't care about stack 1. Okay, we care if the elements are present in stack 2 or not. If the element is present in stack 2, just pop that. That will be the first element. If it's not present, then we'll empty the stack 1 and do the stack 2. Okay, so that's what we have been doing in stack 2. Well, not equal to st1 dot empty, int equal to st1 dot top, st1.pop st2.push a. Okay, we are emptying the stack 1 and putting in the stack 2. Else, so if st2 is not empty, then what we are doing, we are just popping out the first element only here. We are doing st2.top st2.pop. Okay, so why we are doing this? Suppose we have push 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 pop push push. Okay, now we have 1 2 3. Now we need to do pop. So what we'll do, stack 2 is empty, right? 3 2 1. Now we'll pop the first element. Okay, now if we do pop again here, okay, if we do pop again here, do we need, like, do we need again here, do we need to empty this stack? We don't need, right? We need the 2 element only. The 2 will be popped correctly. Okay, we no need to consider this stack anymore. So let's say push push, let's say push 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 pop push push pop. Okay, what will we take? We'll take 1 2 3. Now if we do pop operation, we are eliminating this stack 1, it will be empty. Okay, and all the elements will be here, 3 2 1. Now we are popping the first element. Now we do push push. Now the push will be here only, right? Push will be 4 5. Now pop. Now I told pop means we need to empty stack 1 to stack 2, but you can see here in the stack 2 there are elements 2 and 3, right? The answer should be 2. If we empty the stack 1, then it will be like 5 and 4. The answer will come 4, but 4 is not the answer. We need to empty the stack 1 only if the stack 2 is empty. Okay, if stack 2 is not empty, then we can just return the top element, that will be the answer. So that's what we have been doing in the code. If stack 2 not equal to empty, okay, if stack 2 is empty here, then we'll empty the stack 1 and put everything in stack 2 and pop, or else just ignore and return the top element here. Okay, peak. Now peak, now we have two stacks here, suppose 4 5, and we have 2 3. This is stack 2 stack 1, right? Now what will be the peak operation? The top element, the top element will be, if stack 2 not equal to empty, return st2.top. That is the answer, right? So if stack 2 not empty, we will return here only. The answer will be the top element. The answer will be 2. So if stack 2 is empty, suppose there is no element in stack 1, what we need to do? The same 1 2 3 is there, right? The peak element would be the answer 1, right? So to find 1, we need to do this again. Like we 3 2 1, we'll empty the stack, we'll pour it in the second stack, and we'll return the peak element as 1. Okay, so instead of doing this operation, instead of emptying out the first stack to find the peak element, we are keeping a track of the front variable. So we are taking one variable front and we output it here only. Okay, return front. So here you can see, if stack 1 is empty, if stack 1 is empty in the sense there is no element in stack 1, so the first element would be front x only. Then in the peak operation, what we are being doing here, if stack 2 not empty, return stack 2. If it's empty, then instead of doing the whole operation, we'll return the front variable. Okay, this is a nice optimization that we have been doing. So that's for the peak. And for empty, empty is easy. If stack 1 is empty and stack 2 is empty, return true or else return false. So this is the optimized solution where we use two stacks. We use one front variable and we utilize these stacks properly to implement a queue. I hope you understand my solution. If not, just do it yourself, do a dry run, take few examples, you will get it properly. Thanks for watching my video.